In this video, we're going to look at ice tables. We're going to be solving for the equilibrium concentration when we are given the initial concentration of one or more reactants and the equilibrium constant. In this example, we have the question, 2 moles of hydrogen gas, H2 gas, and iodine gas, I2 gas, are placed in an empty 5.0 liter container. Determine their concentrations at equilibrium given, and our equation is hydrogen gas plus iodine gas forms 2 hydrogen iodide gases with an equilibrium constant of 3.82. So we're going to write our ice down the side, initial change in equilibrium. And this table has to include molar concentration. So we can't use the numbers directly given in the question because we're given moles. So to find molar concentration, we'll do moles divided by volume. So we have 2 moles of our gases, and we're going to divide those by the volume of the container, which is 5 liters. So gases will fill the container, so the total container is their volume. So we get 0.40 moles per liter. We can fill that number into our ice table. So we have 0.40 moles per liter of hydrogen, 0.40 moles per liter of iodine. And we start with an empty 5 liter container, so we have 0 moles per liter of hydrogen iodide. We're given a KEQ value but no other information, so we need to get to a point where we have something to fill in for our equilibrium concentration so we can write an equilibrium expression. We're going to use our initial concentrations to look at the change in our values. So the change in hydrogen is going to be negative x. It's going to be negative because we start with some reactant and we start with 0 product. So we must decrease our concentration of our reactant and increase the concentration of our product. So there's a 1 in front of the x because there's a 1 in front of hydrogen. There's a 1 in front of iodine, so our change of iodine will be negative x as well. There's a 2 in front of hydrogen iodide, so our change for hydrogen iodide will be positive 2x. So our coefficient matches the coefficient for x. So we can now add down this column to get our equilibrium concentrations. So for hydrogen and iodine, it's 0.40 minus x, and for hydrogen iodide, it's 2x. So what we're going to do now is we're going to plug these expressions or these numbers into our equilibrium expression. So KEQ, so it's our products, which are hydrogen iodide. There's a 2 as our coefficient, so we're going to raise that to the power of 2. Divided by our reactants, hydrogen gas and iodine gas. Neither has a coefficient, so there's no exponent used. So we can plug in our numbers, 3.82 equals, so hydrogen iodide is 2x, and that's going to be squared. And hydrogen gas will be 0.40 minus x. And iodine gas will also be 0.40 minus x. Because those are the same, we can simplify this expression and rewrite this as 2x squared divided by 0.40 minus x squared. So having the squared on both terms allows us to take the square root and avoid using the quadratic formula. So in this course, you're not expected to know the quadratic formula. So we're going to just rewrite this now as 3.82 equals 2x squared divided by 0.40 minus x squared. So we'll take the square root of both sides. That will cancel out that x, or the squared over our x components, or x variables. So The square root of 3.82 is 1.95. I've rounded here, but I won't round in my actual math in my calculator. And the square root of 2x squared is 2x. The square root of 0.4 minus x is squared is 0.4 minus x. So to rearrange this equation now, we need to isolate for x. So we're going to take this denominator and multiply it up by 1.95. So I'm going to show all of the steps in this math just so that you have an example fully worked out. So we're going to multiply that by the entire term, 0.4 minus x. That's going to equal 2x. And now we're going to distribute that 1.95 into the brackets. This will allow us to move x by itself separate from the 0.40. So we get 0.78 minus 1.95x, and that's going to equal 2x. So now we want to get all of our x terms together. And so we're going to move or add 1.95x to both sides of the equation. So 0.78 equals 3.95x. We're going to now divide both sides of our equation by 3.95. And that's going to give us x equals 0.198 moles per liter. This is not the answer to the question, as the question is asking for equilibrium concentrations, and we have simply solved for the change in concentration for hydrogen and iodine. So we need to plug this x value into our expressions we have at equilibrium. So 0.40 minus 0.198 gives us a molar concentration of 0.20 for hydrogen gas at equilibrium. And for iodine, it will also be 0.20. And so you can summarize the answer here by saying that the equilibrium concentration of hydrogen and iodine is 0.20 moles per liter. And that would be the answer fully to that question. In our second example, our problem is 5 moles per liter nitrogen gas, N2, and hydrogen gas, H2, are added to an empty flask. What is the equilibrium concentration of ammonia gas, NH3, if the equilibrium constant for the reaction is 6.4 times 10 to the negative 7? So the first thing we're going to do with this reaction is write out our balanced equation. So nitrogen gas plus 3 hydrogen gas form equilibrium with ammonia, and we'll have 2 ammonia gases. So we have our equation, so we can write our ice table down the side, I, C, E. So in our question, we're given the initial concentration of nitrogen and hydrogen gases. So we can fill this information into our ice table. Remember, it always has to be molar concentration in our ice table. Because we're told that the flask was otherwise empty, we know that the initial concentration of ammonia is 0. In terms of change, we don't know yet. We have no other information, so we have to fill out the rest of our ice table with X's. We know that the reactants will decrease in concentration because we start with only reactants, and our products will increase in concentration because we don't have any products to start. So the change is going to be negative X for nitrogen, and this is because nitrogen has a coefficient of 1, and so X has a coefficient of 1 as well. The change for hydrogen will be negative 3x. Hydrogen has a coefficient of 3, and so X also has a coefficient of 3. The change for ammonia will be plus 2x. And for the same reason, ammonia has a coefficient of 2, so X has a coefficient of 2. So now we can write our equilibrium concentrations in terms of x. So we have 5 minus x, 5 minus 3x, and 2x. So once we've done that, our next step is going to be to put this into an equilibrium expression. So our equilibrium expression for this reaction is KEQ equals NH3 squared over nitrogen times hydrogen, and hydrogen will be cubed. So we can plug in our numbers now and just have a look at what we're working with. So we have 6.4 times 10 to the negative 7 equals 2x squared divided by 5.0 minus x and 5.0 minus 3x cubed. This is challenging to solve for. So if we look at this equation here, we're going to end up with a power of 4 on x at the bottom. That is not something that we can easily solve just by taking the square root. So we're going to employ a little trick, and that trick is using an approximation. So we are going to investigate the initial concentration, so our initial concentration of one of our reactants, so 5.0 moles per liter, divided by our equilibrium constant. And our equilibrium constant is 6.4 times 10 to the negative 7. So 5 divided by 6.4 times 10 to the negative 7 is 7 million, so 7.8 times 10 to the 7. We want to compare this ratio of the initial concentration to 1,000. So if the initial concentration divided by K is greater than 1,000, then the change in concentration is negligible. And so what that means is that when we write 5.0 minus x, that's going to be approximately equal to 5. And 5.0 minus 3x is also going to be approximately equal to 5. The reason that we want to use this approximation is now we can rewrite this expression, 6.4 times 10 to the negative 7 equals 2x squared over 5 times 5 cubed. This expression is now one that we can easily solve using a square root. And so anytime you run into a question where you end up with a quadratic formula or a cubic, check if you can use this approximation method to simplify your math. So next up, we're going to rearrange this equation for x. So x is going to equal 6.4 times 10 to the negative 7 times 5.0 to the 4th. And we'll take the square root of those numbers, then we will divide by 2. So if you're not sure how I got to that rearrangement, take a few minutes and make sure that you're able to do that algebra, because it will be very important to be able to do math like that going forward. And we get x is equal to 0.010 moles per liter. So our question was asking us to find the equilibrium concentration of ammonia gas. So our equilibrium concentration of ammonia gas is going to equal 2x. And so that's going to equal 2 times 0.010 moles per liter. And so this equals 0.020 moles per liter. And that is our equilibrium concentration of ammonia gas.